Greetings. This is the first of my Patch a Day series. I'm planning on making 365 of these if the year allows, and I'll update 7 a week, as one per day would be kind of impractical. If you have any ideas of things that you'd like me to cover, things you're unsure of, please message me or leave a comment on the YouTube channel so I can take care of it. First thing that today I'm going to create what might be called a color organ. It might not be called a color organ. You can look at what a color organ is. You just type that into Google or Wikipedia. Anyway, I'm going to take sound input and turn it into colorful images or something like that. So the first thing I'm going to use is audio input from my microphone, so I'll need one of these Easy DACs. All right. Next thing, I'm going to use an object called Sigmund, which you won't have installed, chances are. So if you don't have it installed, go to Google, search for the Sigmund object. We can zoom in and see exactly how that's spelt, just like the famous psychoanalyst, and I guess that's where the idea came from. Yeah, type Sigmund Max MSP into a Google search and you'll find it's the place where Miller Puckett and Ted Appel, well, Ted Appel's the one who created the objects for Max MSP from Miller Puckett's original code for PD. All right, and the other thing, first thing's okay, so we're going to start off with the Sigmund object, and I guess we'll go to the bottom end of this thing and fill in the gaps. The other object we're going to use primarily to create the image is the JIT.matrix. And the JIT.matrix usually needs some arguments, and it does in this case. So we're going to make a 4-plane matrix of type char, and it's going to have 4 cells on the x-axis and 4 cells on the y-axis. Okay, so Sigmund, let's have a quick look at the help for this. If you have it properly installed, you could either have the Sigmund object, the MXO, and the max help objects, max help patch. You could have those both in your directory that you're working in, or you can install them into the Cycling 74 folder in the Max 5 folder in the world. All right. So here we're going to need some arguments. Let's just look at the help to see what those arguments are. You can see Sigmund is a sinusoidal analysis and pitch tracking, and we can just have a look at the sinusoidal part of this thing where it says that you can track a number of peaks. All right, with these arguments, I'm just going to copy these arguments. N peak, at n peak is the attribute, and n, the number of peaks is 10 in this case. Okay. So I'm just going to paste those arguments in here. Saves me some typing. And I'm also going to change this number of peaks to 16. This is the reason I started off with a matrix of 4x4. It's because we're going to use the 16 peaks from Sigmund. 4 times 4 is 16, in case that was eluding you. All right. Oops, so I guess we'll keep the patch for the help open here and notice that what comes out of Sigmund with these peak tracking is first a value that's being routed in this case of the peak number, and then the next 2 numbers are the frequency and amplitude, which are the ones we're going to deal with, and we don't so much care about the cosine and sine components. All right. So to create, to take these, first let's just to take the peak number and turn it into something that's going to be useful as setting a value, setting a cell in the matrix. Again, if we look at the help on the JIT.matrix, we'll see that the message set cell followed by in most cases, two numbers being the X and Y cell number, and then val with a list of alpha RGB or whatever kind of values you're using, is the way to set cell values in a JIT.matrix. So I'm going to first off take these 16, the peak values, and use those. Actually, the very first thing I'll do is create TBL for trigger bang list, because the first thing we're going to want to do after we've created some kind of cell values is to bang the matrix for it to output. The thing that I'm going to use for the getting those getting those values into the JIT.matrix is sprintf, and as we saw, the word set cell followed by two values, %LD for the X and Y, and then the values. We're going to take we'll set the alpha to be constant, and then we're going to take %LD for what would be the red, but we're not going to use it as red. We'll see what we're doing later on. 255, a constant for what might be green, and then another value for what might be blue in a RGB matrix. Okay, so instead of using RGB, I could have said this before I'd created this, but instead of using RGB, we're actually going to use HSL, which is hue, saturation, and luminance. And if you want to look it up on Wikipedia, there's a good article there about what HSL is about. That's really what we're going to use this time, just because we want to take a value that's frequency and use it as a kind of, well, a range of values instead of, and that works really well for hue, because, so yeah, the color then will correspond to the frequency in some meaningful way, or perhaps less than meaningful. So let's take this list that we have coming from our Sigmund. The first number is the index value, second number is frequency, and this third value is amplitude. We'll take these, and to get these x, y values out of here, I'm going to divide by 4 for the x values, and then I'm going to modulus 4 for the y values. That makes some amount of sense if you think that you've got values coming out of here, through here that are 0 to 15. This is going to produce zeros for every, zeros through 3, and then 4 through 7 will be 0 to 3 again, and this is going to be 0 to 3 for each value coming in. So I suppose it's a way of just using changing 0 to 15 into a series of cell numbers for the matrix. Okay, then for the frequency, I think we want to do some kind of linearization of a logarithmic frequency range, which if we make a new object, F2M would do that quite nicely. You can have a look at the help on F2M, and if you want to look clever, I suppose you could use this, which is more accurate than F2M, which is an expression. Yeah, I might copy that and paste that in my patch to make me look like I know how to do some maths, in case anyone ever sees this patch. Alright, and I'm going to hook that in for my frequency. Actually, I might use, because we're going to deal with values 0 to 255, I'm also going to actually multiply that by 2. Very good. So yeah, I mean 0 to 127 is typically MIDI, which is what this will produce, and multiply that by 2 to get 0 to 255. Now I guess the amplitude thing, I suppose we'll do, let's just try it with just some randomness here, times 200, let's say. And let's just put that in there. And just to see what's going on here, I guess we're going to want to use a JIT.p window, and we'll take our JIT matrix output and stick that in there. All right. And let's have a look at what we got so far. If we turn on our ADC, you can see it's not easy being green, and this proves the point. Well, it's not being easy being green or yellow. The reason why we've gone down this road is because we're going to actually use this JIT.matrix here as producing HSL values, and to produce translate those into something that you can see that makes sense. You're going to need to use a JIT.HSL to Luma. I mean HSL to RGB. Sorry. And we'll see how that looks. Just plug it in. Okay, nothing very much there. You can see if I get very loud, we get something. Or I guess we could multiply this by more. So we add another 0 on there and we get something more. Then it's really easy to overload and get white here, meaning that the Luma value is over the top. If you want to just compress a range of values, which is what I think we want to do here, I think the way I like to do this is using the POW object. I like to think of POW as being an easy way to just new object, N for new object, POW. If you do POW 2, so you're raising, that's basically squaring something, you do what I would call compressing a range. Well, it's only if it's 0 to 1, which is why 0 to 1 is such a helpful range of values. You'd be basically compressing the range, but we want to expand it out, so instead we'll do something less than 1 for the power, which if you remember anything about maths, in high school, maybe you never learned it, but it's basically doing a root instead of a square. That looks like it's a bit much all around, so we'll take something off the zeros here. Okay, that looks more like what I would like. Yeah, it seems to at least correspond somehow to the sound I'm making. Wee, ooh, ah. All right, if you like, if your family thinks you're a complete nutter, which they probably do already, then you can make sounds like I do when I'm testing this. The other thing I might do is to slow this down and make it a little bit more presentable, is to use a JIT.slide, which if we get the help, so we can get the inputs into this thing, we can just copy this with the slide up, slide down. I do this for most jitter objects. Open up the help and copy the parts of it that actually do the change the values, change the parameters of the object, because who wants to deal with remembering how to make all this stuff? So I'm just going to copy this much of it. Again, just drag across what you need, copy. I'll close that patch and I'll just paste these guys in here. And this might make it just look a little bit, well, what JIT.slide does is an average for each cell in the matrix over time. So they'll just tend to move a little slower. We could slide it up and down, which is a, well, yeah, okay. So wee, ooh, ah. And you can play around with this and you'll notice that you get a different kind of color for each sound that you make, or a different series of colors. And that's probably about as much as I need to say about this piece, this patch, and I'll check you next time.